Yaskawa.
Good morning, everyone, and welcome to another Yaskawa Web Cafe. My name is Doug Meyer. I'm with the Applications Department here at Yaskawa, and today our topic is going to be understanding PackML. There's been a lot of talk about PackML recently, and the marketplace is certainly becoming more and more familiar with this term. Customers are asking for it. So we thought we'd take a web cafe here and reintroduce this to our channel so that you might understand PackML a little better and be prepared for these type of questions. So first, a few housekeeping items. Our legal department compels me to say that we will be describing some free code that's distributed by Yaskawa in the form of toolboxes and templates. That's really open source code, and Yaskawa makes no specific or implicit guarantees or warranties on this functionality. So ultimately it is up to the end user to apply whatever toolboxes Yaskawa supplies to the machine and verify its operation. That being said, we feel our toolboxes do function very well and very handy in getting people started in their applications. And also, as we typically do for web cafes, all attendees have been muted, but please do use the webinar control box to type in questions into your chat window. You can type questions, comments, issues, things like that if you have any problems. And I will try to stop in between sections and answer some of those questions. So, talking about PackML in general, I always like to start with, your basic questions. What, why, who, things of that nature. So let's talk about the why first. And why should somebody be concerned about PackML? Why would they want to use it? And the fact is, PackML addresses certain business needs. And one of those needs is to define and provide a consistent look and feel to the operator or technician. A lot of cases, these are maintenance people. They have to be able to service this machine, and they need to know how to access it. Operators need to know how to use it. And if we can provide that sort of common look and feel, then it's a much smaller learning curve for these people. It also provides a foundation for vertical and horizontal integration. And what I mean by that is machine to machine, and then within, for instance, a packaging line, and then up to some sort of data acquisition system. So we're talking about a foundation that can provide standard information into and out of the machine. It also drives consistent end user specifications. And these specs are more function-based than hardware-based. So what we see in the industry is a little bit of a paradigm shift, if you will. It's a little bit of a trend where large end users are saying, okay, we don't necessarily want to lock ourselves into a particular control platform or a particular piece of hardware. What we're looking for is improved functionality. But at the same time, we have these concerns with our maintenance group and training, things of that nature. So we need it to be able to drop in. So what PackML addresses then is the need for the end users to be able to apply equipment that may have different control hardware platforms, but still integrate those easily within a line. And ultimately, it should result in faster software development time, helps lower the cost of the machine, improves profitability, all those kind of good business reasons. So what is PackML? And officially, it stands for Packaging Machine Language. It was developed by the Organization for Machine Automation and Control starting in the early 2000s. And specifically, the Packaging Workgroup subcommittee. It's known officially as an ISA spec, and there's information on it on Wikipedia. So we'll take a quick jump over there. You can take a look at the Wikipedia page. I won't spend a great deal of time on this, but what it does show is mainly the history of where it started, why it was developed. You see, it started actually back in the 80s. A little bit of background here on the ISA model. We'll talk about that some too. and through its different iterations. We are actually now on PackML version 3. So good information here on the development of PackML as a global standard. As I mentioned, we're working with version 3 that was released in 2008. Now, combined with another specification called ISA S88 Part 5, or Make to Pack, the PackML approach provides a consistent architecture for machine programming, mainly for the packaging industry to follow. So what is PackML really? And I don't mean really like the Saturday Night Live, you know, really? Really? I don't mean it that way. What I mean is, in reality, PackML is a programming methodology oriented around a state transition diagram. And it's my opinion it can be applied to really any automated machine or process. And it contains 17 predefined machine states that we'll go into detail about, user-definable modes and configurable mode switching states, a set of tags that goes with it. And a good ancillary feature of the PackML spec is a spec for naming conventions called pack tags. And they follow a structure type format. So for instance, PML-C stands for control commands. And here's a couple examples for you. There's administration commands and status commands. So they're broken out into these 3 main categories. They follow the dot type of nomenclature that you may be familiar with our use of our structures in IEC 61131-3. And the Make to Pack provides a modular programming architecture oriented around the concept of what we call equipment modules and control modules. In addition, it has hooks for a very important term that end users in particular are very concerned with, called overall equipment effectiveness, or OEE. And OEE is a function of mainly of availability, performance, and quality. They're measured in different ways, but they come up to multiply together to form a number of how well the equipment is doing. It's very important. So I'll show you some of those hooks. It also has provision for better root cause analysis for event handling. And by events, I mean faults or alarms. And what companies are typically concerned with is the concept of what's called a first out fault. They want to know what the root cause was. I mean, you may have a condition, the machine stops and it shows 10 different faults. Well, that's not very helpful all in itself. You want to know which one happened first. So it does that. It also provides for flexible recipe schemes and hooks for other MES, Manufacturing Enterprise System data. So who should use this PackML? And again, it's my opinion that even though the nomenclature is oriented specifically to the packing industry, PackML can be used by anyone who is doing some sort of complete machine control. Let's take a look now at the defined PackML machine states. And this is what's known as the PackML state diagram. There are 17 machine states, and I want to point out a few things about this chart. First of all, the colors. So what we have here, I'll start with the green ones. The green are known as acting states. And they're the ones where things are happening, they're doing something, they have the ing at the end of it typically. And that's where you find most of the code, the active code of your machine being put. The orange ones are known as wait states. So these are states where the machine is essentially sitting there waiting for some transition out of it. Like for example, you might be sitting in the stop state. It requires a transition called reset to move on and do something until that state is complete, and then it sits in the next wait state. And then the last one, that blue one in the middle, is known as a dual state. Its name is execute, so it is actually acting and doing something, but in a lot of applications it may essentially do that forever. and never complete until it aborts out or something like that. So that's why it's known as a wait state. Another thing I'd like to show you then is the transitions between them. So you have all of these states, and you have defined transitions and specific ones, like moving from aborted to clearing requires a transition called clear. Moving from idle to starting, a transition called start. So you see that the flow is very well defined around here. You can't go just anywhere from anywhere. So that's important from a machine control standpoint, because half the battle of building a good solid machine control is preventing going somewhere you don't want to go. And PackML already defines that in our template, which I'll show you in a little bit here. It already handles those exact transitions and forces you to go through this specific flow. There are only two where you can jump out. A stop transition will jump directly from anywhere to the stopping state, and abort, of course, will jump anywhere into an aborting state. The last thing I would like you to take away from this is that there is nothing in this diagram here that is packaging specific. And that's why I make the statement that this type of program control architecture can be applied to any machine. I will also mention that there's these two branches here for suspending and held, and there's a subtle difference between them. Suspending is the suspending branch is intended for those cases that happen during automatic operation, where the machine is executing, and then say it becomes either blocked or starved. So it may be starved for raw materials that are coming in, and so it has to go into a suspended state. And when materials are available, then it resumes execution. Or it may be blocked by an outgoing process, something downstream. So those are a couple of important things to know for some of the data collection in their OEE system. How is this machine performing? Is it the bottleneck in the line, or is the bottleneck somewhere else? Where is the bottleneck? And by comparing these blocked or starved states, they can zero in on the issue. The held branch is very similar, but this is more of an operator-induced type of hold, like hitting pause or intentionally blocking incoming product even though it's available. Maybe they put down an extra gate and prevent it from operating so they can do something. So technically the machine's ready, but the operator is preventing it from going on. So again, this type of diagram, nothing packaging specific. You can use this for any type of machine control operation. So now that you know what it is and why you want to use it, let's talk a little bit about how it can be implemented. We find that there are three main steps to take when you design a PackML implementation. And first one is to choose the PackML modes that you want to use, what you want to name them. Number two is to assign functionality to those modes, and in particular to each of the PackML states. And then the third step is to modularize your machine code to match the physical and functional configuration of your machine. You really want your code to line up with how the machine's put together. It really enhances the troubleshooting capability. So let's address these in order. First of all, the PackML modes. So version 3 allows essentially for an unlimited number of modes. And here's some of the common names that you might include. The most common, of course, the top two being automatic mode, manual mode. But it's really up to the user. You see in this little piece down here at the bottom of the slide, there's an initialization file, and we allow technically up to 32 mode names. So you could have 32 modes. You just free form call them what you want. In practicality, probably best to stick with a few, representing some of the key modal operations of your particular machine. Next is to choose the mode transition states. And although there's some common ones, maybe there's, again, it's up to you. So let's let's say that we have an auto mode in our project here, and all of the states are active. And then we also have another mode, and we'll just name it dry run. But in this case, we can choose to disable some of the states within that mode. And we're going to disable our suspending branch and our holding branch because we're really not running any real product. So this is just a test run. And say we have another mode. Okay, so we have 3 modes, and you can kind of think of these as floors in a building, for instance. They're layers. And if we're going to go from one mode to the other, we need some sort of stairwell. And so this stairwell, you can think of it that way, and these are the mode transition states. And typically, you want to set them up at some condition where the machine is quiet. Some very common ones include aborted, stopped, or idle. These are states where the machine, first of all, is in a wait state. It's not doing anything. And they're also in a nice quiet condition. Maybe the servo axes are disabled, for instance. So freely definable. You can choose only one. You can choose many. You can choose to go anywhere from any place if you like, but usually limited to these 3. Next is to assign functionality to the states. And although PackML version 3 has a great definition of the flow, how you get from one state to another, it doesn't really, in a detailed way define what happens in that state. And there's a couple of key questions, and I'll list them here. First of all, when we have a motion application, if there are servo axes, where are they enabled? And where are they disabled? I've seen some applications where, of course, they're always disabled and aborted, but in particular, this stopped state I've seen it go both ways. Some applications want the servos enabled in between, say, during this clearing function, when you go from aborted to stopped. I've seen other applications where they prefer to put the enable in the resetting state when it goes from stopped to idle. So it depends what you want to do in the stopped state. So that's a key question. Another one is where's homing performed? Some applications have put it in the resetting state. Some have put it in the starting state. Those are a couple common places for it. How about cycle stop? Cycle stops can be a tricky one. If you notice, the normal stop transition will go to this stopping state, but it also ties into your decision of where the axis is disabled. So I view a cycle stop as just stopping the machine, but everything's still kind of ready to go, enabled, things like that. So if you go to this stopping branch and you've chosen that we're going to disable our servos in there, well, then that's not that condition. Another option is to use the completing branch to do a cycle stop. And I've actually done an application using that successfully. It seems to work pretty well. And it takes a different branch. Instead of aborting out and winding up in the stopped wait state, it goes through completing to complete, back through resetting, and then it's sitting back at idle. So it depends where you want to end up, how you want to implement your cycle stop. Recipe updates, do you do that in starting, resetting, at any point, things like that. So, several key design questions need to be sorted out, and the point is that going through that exercise will allow the company to kind of establish their own conventions, create some strategic benefit, something that is good for the marketplace for their particular product. And then it'll serve as a communication tool between their engineering, their sales, their technician, all those groups that are all stakeholders in this process, particularly for OEMs, of taking this machine and this machine functionality and installing it successfully at a customer. The third step is to modularize your machine code. And we put up this, you may have seen this on the wiki page, but the PackML fits into an overall physical hierarchy, starting at the global enterprise level. And picture yourself as an executive, all right? You want to see how how your business is performing. Maybe you're the production, global production manager. So you want to drill into a site somewhere in the world, go to a particular factory, down to a production line, see how these new case packing machines are working, and you want to zero in on a particular one. You can do that if it follows this type of convention. But for the purpose of our coding, we're mainly concerned with the bottom three levels, starting at the machine, which is known as a unit or a unit machine. Inside the machine, you have one or more pieces of functional modules. We call those equipment modules. And those carry out some sort of finite number of activities. And then within the equipment module is what's called a control module. Technically the lowest level of control, where a single function is executed. The commands are likewise modularized. So when you create your levels, your hierarchy levels of a unit machine, equipment module, control module, you might have, say, a line controller, which has the highest level of commands, and you see that those commands get distributed down all the way to where the action happens, and then the status of that gets rolled back up and summarized at least twice, once at the equipment level and then once at the entire unit machine level. Now here's a few tips about code modularization. Don't go overboard with control modules, number one. When I talk about a single function, what I don't mean is every single device, like every air cylinder needs its own control module. That would be excessive. You could have hundreds of them. So we want to relate them into a little bit larger groups than single devices, but still trying to get as close as we can to a particular piece of functionality. And you want to focus the modularization on groups where the reporting of PackML state completion is needed. So if it doesn't impact moving on to the next step of your diagram, completing some state like resetting or completing a state like clearing, then don't put it as a specific control module. So if there's little or no impact, roll those into other ones. And try also to avoid using a single control module in an equipment module. That's a little bit of a waste. Instead, consider building that control module into another piece of equipment. And the fourth tip I have for you is to include, kind of keep multiple devices together if they represent some kind of linkage. So for example, you have a couple of axes that are cammed together, or one passes something to another. It's important that they're both active, ready, enabled, things like that. So you can include them into essentially one type of functionality or one control module. Maybe the best way to illustrate this is to go through an example. So let's say we have a case packing machine. It's got 9 servo axes and 7 key functions. So here's some of the functions, like feeding cases, opening up the cases, sorting out bags. This might be bags of whatever product is coming in. And then the servo axes, one opens a case, for instance, one transfers a case, might have 3 conveyors here. And then other ones on the back end for closing the case and ejecting the case out the machine. So 9 axes, 7 key functions. But keeping in mind the tips that I just explained to you here, we see that if we divided this up into 7 equipment modules, and each one had a control module within it, we'd find that 5 of them would only have one control module. So maybe we should rethink this a little bit and see if we can combine these in some way. So here's another way to look at this. Let's say we have our machine, and we instead divide this up into 2 main pieces of equipment. One equipment is going to handle bags of product, and the other piece of equipment is going to handle cases of product. So this might be very handy because you could disable one or the other during your development and debug mode and just handle one or the other. So from a modular standpoint, that seems to make sense, and it reduces the number of equipment modules we have into two main functional groups. Underneath that, we can define our control modules. So on the bag handling side, we would have two, one for sorting out bags, one for loading bags. In the case handling, we have a few more. So we would have 5 control modules. So in this way, we avoid having an equipment module with only one control module. They're split into logical groups, and then from then on, I'll show you where the servos are. And you see there's at least one in each one of them, but some of them, like the bag sorting, because these, for instance, these 3 servos all work together, they can be logically defined as one control module. You're never going to have one operating without the other 2. They all depend on each other. So, how about alarms? So when we say alarms, there's a lot of terms for that. Alarms, warnings, errors. We just speak of them in terms of events for PackML. So what do we have for event handling? Well, much the same way that the commands flowed. Individual events such as alarms or warnings get reported up, and they get summarized at the equipment module and then again at the unit machine. And then they can be displayed to the operator, the list can be reported, and then reset from the equipment module, distributed back down. So when we do it in this way, it does help identify where the alarm came from, which equipment module, and which control module. It helps zero in on the code where the problem might be. So PackML for each event provides a defined structure for the alarm array, provides an ID number, a message, a further verbose description, and also allows for a category. The category would be severity. Do I need to stop immediately? Could I just do a cycle stop? Things like that are descriptors that could go in a category. And depending on the capabilities of the controller and the HMI, what you do with those, how you store and report the alarm history, you have a couple of options. You could store it all in the controller, which we've done for an application. You could simply pass an event number to the HMI and let the HMI perform a lookup and keep its own history. A lot of HMIs kind of have that built in. Or you could do some combination. We've done them all 3 ways here at Yaskawa. All right, so let's move on to tools and templates. So what do we have available for implementation to help you get started? The first place to go is the OMAC website itself. That's where you will find the PackML actual specification and implementation guide. You can get to it right at omac.org. We have the Yaskawa PackML toolbox, which contains the state control diagram, other control and status management functions, and you can download it right from our yaskawa.com IEC toolbox page. I'll go right here and you can take a look at this here. So you'll find this right here in our PackML listing. Right now we're on PackML Toolbox version 202. We will be adding a description here very shortly, and also including the link to the template, which provides you with example structures and example equipment and control modules. You can search for PackML on the website or click here to download this. Right now it's PackML version 201. So this actually includes the PackML toolbox inside of it, so if you download the template you get the toolbox also. And I think what we'll probably do here very shortly is make that change on the website so that this actually downloads the template. Okay, so what's inside there is the heart of the system, which is the state diagram. And I'll show you what's inside the template. I'll move over here to MotionWorks IEC. It is this template is designed to work with the Pro version of our software only because it requires multitasking. So there's a couple key things that are provided in this template. First of all, two equipment modules, generic equipment modules, have been defined, each of which have 3 control modules inside of it. And here's the other one. It also contains some initialization code, like PackML initialize, which provides some of the initialization of the state names, of your mode names, of your mode transitions, and at the end, how many enabled equipment modules you have, and for each one, how many enabled control modules are inside of it. So the overall template allows for up to 16 equipment modules, each of which could have 16 control modules. At the heart of this is the state model for your unit machine. And right here in this diagram is the PackML state control diagram. It shows up here as a function block, but if we look inside there, you'll see that it is a sequential function chart. And so this is what the PackML diagram looks like in sequential function chart. We start in a stop state, and then depending which transition you get, you can go to the resetting state, the aborting state, or the stopping state. If you move on and get the reset command, you go to idle. If you get the start command, you go to starting. At any one of these, you can go to the aborting or the stopping state. So all this is pre-done for you. All you have to do is give it the inputs, the command to reset, start, stop, hold. It will report to you what state you're in our status structure. It will also report to you what your current state is, what the current state name is, what the current mode is, what the current mode name is. And depending on the mode transition states, it will disallow a change to a mode if you're not in the proper state. So where does it get the commands from? All these commands come in from somewhere. And they come in from this diagram, the UN control inputs page. I'll just show you a few things here. Here's an example of how to do mode control. So say we have a HMI, and we have some selector switches on our HMI for auto mode, maintenance mode, manual mode. All we do is write in the correct mode number into the mode command. It's used by the control diagram. These are also pre-done for you. So we have all of our commands listed here in pretty much a ladder format. So to get the command for abort is essentially tied to an e-stop input. A push button for cycle stop, in this case, would give the command stop. So these are just examples. HMI push button, clear alarms. If we're not aborted, it gives the command to clear. And so on and so forth. So this is the part that's freely available for the user to edit. They would replace this kind of dummy bit here with the actual bit that they wanted to control from their HMI. And taking a look inside of here, one of the equipment modules and the control modules. Let's just take a look at this one here. Inside here is some example of event control. So if you have some alarm condition, you might want to feed that up. Actually, let's look in our equipment module 0. In this position here, we have an example of enabling a servo motor. Okay, so here's a recommended chain, for instance. You may be familiar with the access control block of our PLC Open toolbox. So you see this template actually incorporates some of our other toolboxes, Math, PLC Open, Yaskawa. And you see that some of the inputs to this are tied into our PackML structure. Equipment module 0, command module, control module 0, the command clear goes into the alarm clear. You see some other of these PackML bits tied in to this function of enabling the servo. If we have some sort of an error, these are some of the event handlers. So if we get, for example, a servo pack error, it will take into it the alarm ID and do a lookup and write that into our message structure. So what we can do is automatically with this block take the alarm code, pass that up to the HMI, and also pass the textual description up to the HMI. It's all built in. Okay, so that's some of the basics of what you'll find in this template. The user can, modify the number of equipment modules, control modules, expand them or shrink them to match their application. They can go in and edit the PackML initialize routine to set it up for their application. They can go in and modify the control inputs page to tie it to the real-world I/O and the real-world HMI tags that they use in their application. Okay, so I'm going to skip several of these slides here because I just went through and showed them to you. All right, so to summarize this here, and some of the PackML key benefits are that it provides to you a program architecture. It's a standard global program architecture and programming methodology that does a few key things. It provides a consistent look and feel among your machines. It helps make it easier to maintain and troubleshoot. And it provides some of those common hooks for OEE data collection and analysis. To get started, we have these templates, which includes toolboxes. We have use guides for it. And again, once you start with that, you do need to do some design work up front with these three key decisions. What modes do you want to use? What function is going to happen in each one of the states? And then how are you going to design your equipment modules and control modules to match the machine? All right, that brings us to the end of our presentation. I'll handle any questions that came up.
I think we did.
Oh, okay. Going back to the state control diagram, there was a question about in our transitions, we have names for some of these, like reset, start. Well, how about for some of the acting states? Coming out of all the acting states, you see this transition called SC. And what SC stands for is simply a generic term, stands for state complete. So that's a great question. Let me go ahead and let me go back to one of these control modules here. So say we have our main code. Included with each control module is a worksheet called control outputs. And this is the logic for deciding when that state is complete. So for example, if I was told to abort, then for this control module, I'm looking for this aborting done condition, or any one of my states. I'm looking for this condition to be done. So I just put in the appropriate things. So I'm going to say, okay, well, when this access is turned off and not enabled, I'm going to consider that to be done with the aborting state. That gets fed in to this block here, which is the block that rolls up that status. So it'll say, okay, this control module now is aborting done, and then at the equipment level, this is where the summarization takes place. So all of that individual state complete information gets fed into this one structure here. And then this block determines when all of the control modules within it are done. And when that's done, it feeds it up to the unit machine. The unit machine says, oh, okay, aborting state done, move to the aborted state. Great question. So these pieces of code are already here for you. In addition to, this is where I want to go, the control outputs page. So in addition to tying conditions in the control input side, the user is also tasked with adding any other conditions that would result in one of these states being complete for that particular control module. Good question.
Let's see, you can't web regulation help you kept track of how those three decisions were handled in successful applications. Groups, perhaps future versions. Okay, those are comments. Any farther down?
Okay, looks like we have some very good comments, but that looks to be the end of the questions. So again, I want to thank you for taking some time here to participate in today's web cafe. We hope it was informative for you. We will be posting a recorded version of this on our website under the partner login and perhaps under the YouTube page, okay, at Yaskawa's channel for YouTube. So please look for that. And if you have any other questions, please feel free to email me or our training group with any follow-on questions. Thanks again, and have a great day.